Now that we have the reactions for this beam, we're ready to draw the shear bending moment diagram for it. The hard part is always to figure out what those reaction forces are, because as soon as we find them, shear bending moments are relatively easy. They take practice, but relatively easy. So a reminder, a two-span beam with reactions at A, B, and C. In this case, the spans are equal, and the beam is supporting a uniformly distributed load. So let's draw the shear bending moment diagram. First of all, we drop down lines wherever we have vertical forces in this case that will alter the shear diagram. Then we start at the very right, and we start at 0. And we go up or down by whatever vertical force we have at that location, in this case 28.439. Then we move to the next line, and in order to do that, we go down by 5.2 kilonewtons per meter. So every meter down 5.2, every 10 meters down 52, every half meter down 2.6, and so on and so forth. So if we go down by 12.5, we go down by 65, okay? So if we take this and subtract 65, that gives us 36.561. Okay, right here. And how do we connect the points? It's a straight line. That's because this value ends up being the slope of that straight line. I don't have a straight edge, but this is meant to be drawn as a straight edge, a straight line. You're expected to do so when it comes to submitting anything worth grades. Then at this point, we go up by 73.122. Which brings us to 36.561. So look at this, we went from negative to positive. Okay? Okay? Another straight line. And then to go from here to there, same thing. We go down in a straight line by this slope. So it's going to be 36.561 minus 5.2 times 12.5. And it gets us to minus 28.439, which is good because it matches exactly what we have here. We're going to get to 0. And again, this is meant to be a straight line. You're expected to draw it with a straight edge, no freehanding. And then right here, we go up to 28.439, and we end up at 0. Which is good, because our shear diagram must always close. I've already labeled my shear diagram with units, sign convention, max, min. I'll just fill this in so I can move on to the bending moment diagram. The max shear is 36.561. The min shear is that value negative. Okay. In order to move on then to the bending moment diagram, areas, remember that? So we have 4 areas here, 4 different triangles. One thing before we forget is to remember that wherever the shear diagram passes 0, we drop another line for the bending moment diagram. Okay? So we have an area 1 here, area 2 here, area 3, area 4. And I remind myself, this one's going to be positive, negative, positive, negative. So I don't forget, okay? It's a double check. Now, in order to calculate these areas, I'm going to need the vertical dimensions, the heights, and the widths, or the bases. So we need to figure that out. So we have to figure out x1, x2, x3, x4. Okay. And we'll do that on the side where there's a bit more room. X1, if you remember, is simply the run, okay, where this is the rise, this is the run. And for this triangle, we know what the slope is, so we can calculate what this run, given the rise and the slope. So it's going to be 28.439 kilonewtons divided by 5.2 kilonewton meters. Okay? And this result then will be in meters. And that gives us 5.469 to 3 decimals. Okay. Now that we have that, we can calculate the area. $155.533. Okay. Now for the remainder of these calculations, I won't repeat the units since they're the same, okay, and it will save us time. X2, nice and easy. If we know this whole length is 12.5 and we know what x1 is, we do the difference. $7.031. Area 2 is minus 36.561 kilonewtons times this length. Okay. And I've gotten to this point because I want to point something out. The most common mistake to make when it comes to doing triangular areas is forgetting to do divided by 2. So I forgot to do it up here. And I remember to do it here. Okay? It's a silly mistake to make, and you don't need to lose unnecessary marks for it. So make sure that you don't forget about that. So this is 128,530. And this one is 77.766. Now, area 3 and area 4, we actually already had those values because everything here is symmetric. It just so happens for this specific case, everything is symmetric. So the magnitude of area 3 is the same as area 2. The magnitude of area 4 is the same as area 1. Just have to make sure we do this correctly, okay? Area 3. And a reminder, this is a negative, right? So area 3 is positive, 128.530. And area 4 is negative, so it's that. I encourage you, don't take my word for it, recalculate x3 and x4, and then area 3 and area 4 to make sure this is true. Okay? You don't want to be caught on a test or an assignment where you think this is correct, and then you just assume this is the case. We're now ready, now that we have the areas, to draw our bending moment diagram. We start from the leftmost, start at 0. Any moments here at A? No. So we can move to the next line. And remember, what is the algorithm? It's always previous moment plus area. Okay? So in order to get here, it's the previous moment plus area. So the previous moment is 0. Area 1 is 77,766. So that's where I go. Okay? How do I get there? My shear is going down in a straight line. That means it's a frown. So it's a parabola that faces downwards, like this. Okay? Now I want to move to this next other line. How do I do that? Previous moment plus area. Previous moment, 77,766, plus this area. So that becomes minus 50.764. Now, how did I get the negative? When I add a negative area, right, this brings it down. How do I connect the two? If the shear is going down in a straight line, it means it's a frown. Okay. Now that I'm here, how do I get to this point? Previous moment plus area. So minus 50.74 plus area 3. 77.766, which is what we're expecting, right? Because this is symmetrical, so it should come out to be the same value, assuming we did things correctly. How do I connect these 2 points? With another frown, because the slope is going down from my shear. Okay. Another frown. And then, how do I get to this line? Previous moment plus area. Previous moment plus this area, which is negative. Hopefully, it should come out to be 0. And look at that. It does, right? Which is good because our bending moment diagram must always close. And how do I connect the two? Frown, because my shear is going down. Okay? Now here is another important thing. If I drawn this bending moment diagram to scale, this distance here, where the bending moment diagram goes through 0, should match the distance of the inflection points you found previously in part 1 of this video. Okay? So give that a try, see if it works. We're ready to wrap it up. All we're left to do is to fill in the label of the bending moment diagram. The maximum moment is 77.766. the minimum moment is minus 50.764. And again, this is important because the various curvatures that correspond to those different moments, for example, when it comes to reinforced concrete, will help figure out where to put your tension steel. That's it for this. Thank you so much for your time.